All right, so we finished up the chapter yesterday. So now we're moving on to comparing means. So just like when we compare proportions, we can answer a lot more interesting questions when we're dealing with two different samples and we're trying to compare the differences between the averages of those two samples. So this is going to be pretty cool, and we get the next three examples I get to share with you are from the book. You can kind of follow along with that if you want more details about them, but they're actually pretty cool, and I find them interesting. I think you will too. So the question that they want to answer for the example today is, do name brand batteries outlast generic batteries? And if they do last longer, on average, how much longer do they last in the generic brand? And is the price difference kind of showing that? Would be kind of the next question natural question we want to ask. So if we're paying 20% more for name brand batteries, do they last 20% longer than the generic ones? And if it's not, then is it worth it? So kind of a really cool thing. And I've known people who've had some, kind of conspiratorial theories about how they make it all in the same place and stuff like that. But it'd be interesting. So this is actually a statistics student designed a study to compare the lifetime of these batteries back in 1998. So if you notice in the photo, that's called a Walkman or a CD player. And you used to like put a clip and like attach to your pants, and you would like walk around in public with that. Yeah, I know. In the days before CD players. Yeah. So anyway, days before iPods and phones, smartphones and stuff like that. So it's before the iPhone. Anyway, so they decided they were going to test that. They bought 6 different sets of AA batteries from well-known brand name and a generic competitor. They would test the lifetimes of the CD player playing the same song at the same volume continuously until the CD player stopped. He alternated between each trial to control for changes in performance of the CD player. Like if it got hotter as it went on, how would that change the amount of power that it consumed, or the amount of energy, the rate of consumption of energy, which would be power. All right, yay physics. Continuously until the CD player stopped, he alternated between each trial to control for any change in performance in the CD player. He recorded the results in the table to the right. Okay, so if you're looking at your assignment, you can see the table of all the data. So the first thing we want to do is actually graph out the data to check for any outliers. So that's going to be our first step. So visualizing the data. So it's the same CD player, same song at the same volume, but it was with different batteries. So this would be an experiment, of course. Let's see. So brand name and generic, and you can see the amount of times that in minutes that the CD player lasted with those fresh batteries. With the brand name, we notice that there's actually more variation and a larger range, it looks like, just slightly. And the brand name actually performed less. The duration minutes is less than the generic, which is interesting. The generic was also very consistent. You notice the IQR there, the interquartile range. There also were no values that were outside the first quartile and the third quartile, except these outliers. But the only reason these are considered outliers is because they're beyond 1.5 times the interquartile range, which I can show that real quick. I've gotten better at doing that, so let me see if I can demonstrate that. So if we do the interquartile range 1.5 times, which would be about that length right there, and then I'm going to lock that vertically. And if I add that to the third quartile, you notice how this is beyond that value. And if I subtract it from the first quartile here, notice that is beyond that value as well. So that's a test that they're using for the left and the right fence. And I know I make it look so easy now whenever but I'll fix that when I redo this next year. All right, so we do have outliers, but the only reason these are considered outliers is because of the small interquartile range and the consistency of the generic batteries. So right off the bat, this is interesting because the generic batteries are outperforming the brand name, and they're consistently outperforming the brand name with more consistency than the variation that we see in the brand name. But the next question we'll have is, because this is such a small sample size of only six trials for each one, could this just have occurred by simple sampling variation, or is this a statistically significant evidence to be able to conclude that the generic batteries actually outperform the brand name? All right, so here's our two I guess, distributions going on here and the summary statistics for each one. So if you put those in your calculator and you run one variable statistics, you'll get this information. So the average for the average battery life for the generic and the standard deviation for those, and then the average for the name brand and the standard deviation for that. So do notice we have a larger standard deviation for the name brand, and it's much more consistent, a smaller standard deviation, so less variation for the generic. And that's even with those two supposed outliers. Both of these have a sample size of 6. Let me go back. So next thing we want to know is what is the standard error for each one of these different samples. So we'd find the standard error by taking the standard deviation of the sample, which is going to be 10.3, divided by the square root of n, which would be the square root of 6. And if we put that in the calculator, we'll get 4.2. So I'm not going to put it in the calculator because I'm going to totally save us time. So just go right along with it. So exactly the same thing. Notice that we have more standard error, a larger standard error for the name brand, and that's because there was a larger standard deviation for the population. So this is the difference between doing inferences with proportions and inferences with means. With proportions, the standard deviation is tied to the binomial model, which has the same variation for the same proportions. But when we're talking about standard deviation for samples of means, the mean is not tied to the standard deviation in the formula. We do have the same dividing by the square root of n thing happening here, but besides that, you couldn't have the same mean but larger and smaller amounts of variation in different samples. So we do have just kind of another thing going on when we're dealing with means. Makes them a little bit more complex. That's why we did the proportions first. All right, so here's our two different sampling distribution models for each one, what we would expect for samples of generic. And again, this is not centered at the actual true proportions. This is based on the standard error, which is based on our samples. So we would expect a true proportion, or not proportion, but the true mean to be somewhere between two standard deviations on the sampling distribution model. So you can kind of take that for what it's worth. So are these differences based on sampling variation, or was it actually statistically significant? So what's the probability that two samples with these different sampling distribution models and their own respective standard errors and stuff would have such a large difference? So the first thing we do is calculate the difference between the two. So generic minus the name brand, which we do generic minus name brand, would be 18.6. Typically, you could switch the order of these two. We like to deal with positive values. If I was going to do this again, I would actually probably put the name brand before the generic, and I would switch the order so we get a negative value. And the reason I would do that is because we're paying more for name brand, right? So we would expect it to outperform the generic. It's kind of the name brand's game to lose, right? So the fact that we would have the name brand first, whichever one we would expect to be more first. So for instance, if we were comparing the heights of the average heights of like husbands versus their wives or something, we would expect that the husbands would be taller, right? So we would put the husband's heights average before we put the wife's average height, because we would expect it to be a positive value. And if we got a negative value, then it would be kind of alarming. It would be like, okay, whoa, this is crazy. Just like in this case, if we got a negative value because the generic, which we didn't expect to, is lasting longer on average than our name brand. But keep in mind, small sample size of only 6, right? Okay, so let's write our hypotheses. So our null hypothesis, H naught, is that the generic minus the name brand is equal to 0. So there's no difference between the duration of generic and name brand batteries. The alternative, we're going to do two-sided. We could just do one-sided, but we're just going to say that there is a difference. If we were doing a one-sided test, we would say that this value, the generic minus that, would be less than 0, which we would... we would say would be greater than 0, which would be saying that the generic is outlasting the name brand, because that's what we'd be interested in. So a lot of times you can do one-sided or two-sided. It doesn't, it just kind of depends on the context. All right, so another thing here is that, remember, our null hypothesis is based on the probability. So our p-values are based on a condition that there's no difference between the two. So if there was no difference, what's the probability of a sample difference like we just got? That's what a p-value is. So if we're going to base it on the null, is assuming the null is true, then we would have to actually pull the data together. So what we want to do is we want to take the the total minutes from the generic, the 6 sets of generics, so their average times 6 will tell us back to the total, and then multiply that, kind of weighting the same thing, the average times those 6, and that'll give us the total amount of minutes of playtime divided by the total number of sets, which would be 12. This is pulling, okay, by the way. We've seen this with proportions. We're going to do it again with means, but there's a caveat. We can only do pulling with means when we're doing testing when we know or we expect that the variation in the samples is the same. So our sampling variation was not the same, but if we expect that the populations, because remember, this is just a snapshot, just this quick representative of size 6, right? A sample of 6. If we expect the proportions to be same or very close, then we can go ahead and pull it together. But if we don't, then we can't do this pulling. And we'll discuss that more, I believe, tomorrow when we talk about pulling. There's like 2 pages in the book. You don't really need to know it too much because actually pulling, spoilers, pulling is not going to give us a huge benefit when it comes to inferences with means, because if they do have the same standard deviations or same amounts of variations in their proportion and their populations, then the actual values that we get by pulling is not going to improve it very much. So in general, we're just not going to pull when it comes to means, but with proportions, we always pull. All right, so are the differences based on sampling variation? So if we pull them together, we would see, well, the difference between these two is the Pythagorean theorem of statistics. So this is the standard deviation for the generic, and this is the standard error for the name brand. So we do a squared plus b squared is c squared because we have 2 random variables or random events, and so their variations add, and their standard deviations are going to relate like the Pythagorean theorem. So if variations add, then the standard deviations, we do a squared plus b squared, and that gives us the combined variation of both of them. All right, which is the c squared, in other words. All right, so one of these we'd expect the mean, so the average altogether for all 12 sets of batteries for the whole test was 196. The name brand underperformed and the generic overperformed. So the next question is what is the standard deviation for the difference between 2 samples of these sample sizes and all that great stuff, right? And would this difference be statistically significant? So looks like this might have been slid down. Okay, so it looks like I just didn't adjust that right. So yeah, we should be good. All right, so we've got our 2 standard deviations, 2 different samples, the standard errors for each one of those. So notice that we have a smaller bell curve for the sampling distribution model for the generic. That's because it had a smaller sample size, even though both of these had the same, they both had the same sample size, but it had a smaller standard deviation of the sample. Okay, so what we do for this, and you've seen this before, it's kind of a beautiful illustration, and I teach geometry as well, so I love the Pythagorean theorem, and so like this is just the beautiful marriage of the 2 subjects that I teach, and I love visuals. That's why I'm a huge fan of my smartboard, as you can see. So on this one we have the variation of the sampling distribution model for the name brand plus the random event of the variation of the sampling distribution model of the generic batteries, which would then give us the variation of, or in this case we're talking standard deviation, but if we squared them it works, of the difference between those 2 samples given their sample sizes and their individual sample standard deviation. So a lot of stuff going on there, but a beautiful thing about this, and I'm going to go into it again real quick just because I can, is that these 2, if this was a Pythagorean theorem, that's based on the condition that we have 2 legs of a right triangle, right? And that's how we get the hypotenuse. So these 2 have to be the perpendicular. So if the triangle is a right triangle, then the a squared plus b squared is equal to c squared. Now in statistics, this is only true if the 2 events are independent. So is the name brand performance independent of the generic? And if you think about it, a right triangle, it's independent, right? So if this one was leaning slightly towards the name brand, then that would mean there would be a positive correlation between the 2. So as the name brand performance increased, it caused a drug over the generic as well to also increase as well. And if there was a negative correlation between the two, this is so dope, then that would mean that there was a negative correlation. So as the name brand batteries perform better, the generic batteries tended to perform worse. So the only reason why the Pythagorean theorem of statistics works is based on the condition that these two are independent of each other. So the name brand performance and generic performance are not related to each other. All right, so really cool stuff. I absolutely love that. You get into something called covariance, which is beyond the scope of this course, but it's basically kind of what you think. It's the variation or the relationship between the variation of two samples. All right, which allows us, I believe, correct for some of that stuff. Okay, so our difference was 18.6 in the two means, the mean for the generic minus the mean of that. The standard deviation for the two samples are given there. So to find the standard error for both of those, we do the Pythagorean theorem. So this is the standard error for the generic plus the standard error for the name brand, and notice we're squaring the standard errors, which gives it back to variation. So this is the variation and the sampling distribution model, plus the variation and the sampling distribution model for the name brand. When we add the variations together, because they're independent, then we take the square root of that to get it back to the standard error instead of the variation of the sampling distribution model of the differences between those two samples. All right, that's where we get the 7.29. So next question is, this is the sampling distribution model for the difference between the two samples of sample size 6 of generic minus name brand. And we'd expect the difference to be 0, right? That was our null hypothesis, but our actual difference that we observed, forgot to lock that one back in place, is 18.6, which is a t-score of like a z-score, right? So it's 2.55 standard deviations above the mean, which we would consider unusual. The only thing that we have to look at now is the degrees of freedom, because remember, we're still working with means, and this is going to be a flat degree of freedom, or a flat t model, not so similar to a normal bell curve, because we're not such a small sample, right? Remember Gosset's distribution with his drinks, right? So the question is, where in the world did this degrees of freedom come from? So both of these had a sample size of 6. So if we add them together, we would get 12, and then 1 minus that would be 11, or maybe if we subtracted 2 from it would be 10, but that's not like 8.98. That's really weird. Well, as you can probably imagine, there's a really funky formula for calculating degrees of freedom between the sums or the differences between two samples. So it's not as simple as just adding 6 plus 6 and subtracting 1 or subtracting 2 or something like that. It actually comes from the calculator. The good news is the calculator is going to do it for you every time. You're not expected to know the formula, because the formula is nasty. Do you want to see it? I'm going to show it to you. Brace yourselves. There's the formula. Yeah, that's gross. So you can probably figure out what the variables are talking about, right? So S1 over N1, right? Plus S2 over N2. So this is the variation from the sampling distribution model, right? It's this part right here, okay? So this plus this one, okay? Then we square it, which is going to give us, so variation plus variation squared. What happens when you square variation? I don't know. Okay, and then 1 over the sample size of 1, so this is like the degrees of freedom. So 1 over the degrees of freedom, okay, times the variation squared again, plus 1 over the degrees of freedom times the variation squared again. So I guess I see what's going on here. We do have the sum of the variations squared and then variation squared. So it kind of balances each other out, but then these are being weighted by their individual degrees of freedom. Wow, this is really funky, and I'm sure it's a lot of fun for people to think about, but good news for you is you don't have to do any of this. Your calculator is going to do it for you. But kind of cool to try to wrap your head around what in the world's going on there. Definitely smarter mathematicians than me. So what's the p-value? The probability of that occurring, again, we would have to go to our calculator for that, because we're not using a normal model. We're using a t-distribution, or the family of models, which will give us, I forgot to lock those two together, about 3%. So the question is that statistically significant? So what is the p-value? How do you interpret p-values? P-values are conditional probabilities based on the condition that the null hypothesis is true, which would be that there was no difference. So if there was no difference between generic and name brand performance, then the probability of finding an observed statistic difference of 18.6, like we did here, would only occur 3% of samples. Is that statistically significant? Well, it depends on what you set your significance level at. What's your alpha level, right? 1%, 5%, 10%? That's what we're going to get into next. All right, so this is a gorgeous slide as well. I got some good visuals for you today, which I made I'm pretty much made all of it last year, so whatever. So our null hypothesis that the hypothesized difference between the two samples is 0, so there's no difference. The delta naught is 0. Excuse me. The alternative is that it's not equal to 0, so that there was a difference, and we found 3% to be the p-value. Now, if we're doing two-sided tests, we would have 3% on both sides, right? So our actual p-value would have been 6%, which might have been the difference between accepting and rejecting if our alpha level was 5, right? 5%. All right, so anyway, here's our null hypothesis. We're assuming the difference is 0, and we said that that's had a standard deviation of 5.29. Remember that came from right here, 7.29. Okay, so that's what we'd expect. Our actually observed difference was the 18.6, right, which would be right here. So even if we set our alpha level at 5 or 1%, it would have been statistically significant. But oh wait, this is not a normal model. It's degrees of freedom of 9 T model. So these values are actually going to move slightly to the right. So notice there's not much of a difference between the 5 and the 10% area, but when we get down to the 1%, we actually have to go quite a bit further. So it looks like our level of 18 is going to be a little bit different. So I'm going to set the alpha level, let's say we did 5%, then our value would have been statistically significant. But remember, if we're doing two-sided tests, then it would be doubled and it wouldn't have. All right, now this second part down here is if there actually was a difference. So if there was a difference between the mean performance, then this would be not a type 1 error, but now if we fail to detect it, would be a type 2 error. So what do you think that difference was? Well, again, we don't know what it was. Let's assume that it was the 18% that we had. So I'm going to center it at the 18. So this is no longer true. I'm going to mark it up real quick. This is no longer true because that's not what our sampling distribution model is. That was based on the fact there was no difference, but now we're saying there is a difference. So we can't have a type 1 error anymore. Now we have the power of the test to detect the difference, or the fact that we failed to detect it, which would be when we would be below this level of significance, which would be this left tail here. So if the observed difference of 18.6 was the actual difference, then this will tell us the power of our test in order to be able to detect that difference with our given sample sizes. So if we would have changed our alpha level to 1%, remember it's not this value, but the one further because we're using the degrees of freedom of 9, which came from our calculator, right? That nasty formula, which you guys love. So now notice our power of our test is about 40%. So only 40% of the time, if that was true, right? So if the actual difference was 18.6, then that means 40% of our samples or our experiments, I guess we could say, with given the same sample size, would correctly be able to detect the difference to the point that it would be within 1% significance level. So a p-value less than 1%. Now, if the actual difference was only closer to about 10 minutes, then we'd have even less. But if we allow the sloppier alpha, so we're allowing 5% false positives, or maybe even more like 10% false positives, then all of a sudden we have a more powerful test. So just bringing this stuff up again because it's really good. The difference between our hypothesized value, which is almost always 0, and the actual true difference, whatever that is, and of course, that's like a God only knows thing. But the difference between those two is called the effect size. And ideally speaking, we would have a very large effect size, like let's say 30 minutes. Then regardless of what alpha we picked, even the most strict alpha of 1% false positives, right? We would still have an incredibly powerful test, which would be, even with those smaller sample sizes, to be able to detect the difference between the name brand and the generic performance. The other thing that we can do, what's the answer in statistics? Always a larger sample. As long as we're gathering data appropriately, right? Don't forget that whole unit. But as long as we're gathering it correctly, we can always increase the power and have better statistics by more data. So yeah, just don't forget, it's not the size of the sample, love, but how you got it. Thank you, Austin. Much appreciated. I couldn't help myself. It's late and I'm talking to myself. So basically, if we wanted to also increase the power, let's say we had a smaller effect size. If I was able to shrink this curve here by increasing the sample size from only testing 6 batteries or 6 sets of batteries to like 12, or if I quadrupled it, that would do the square root. That would half the standard deviation here. So if I would have done 24 sets of batteries instead of 6, then this would be half the standard deviation. And so our power would be, instead of being right here, it would be like right over there. And so we would have a more powerful test that way as well. Okay, so almost done. I've been going a long time here, just on one example too. So confidence interval basically uses the same standard deviation for the differences between the two samples. So the Pythagorean theorem statistics, the calculator will do the degrees of freedom for you as well. We use the inverse T model to be able to find out what the critical value is for how many standard deviations you have to go out from the mean whenever you're creating your margin of error. And then with your confidence interval, you take the difference between the two samples plus or minus the critical value, which is this one right here, whatever that value is, multiplied by the standard error, which came from the Pythagorean theorem of statistics. So it works just like you think it does, just like we did with proportions, except now we're dealing with t-values because we're using Gosset's models or family of models instead of the normal, and we'll get a confidence interval, which the calculator get for us anyway. And the calculator is showing that what was our confidence level? Oh, 95. Okay, so we are 95% confident that the difference between the means between the generic and the name brand is anywhere between 2 minutes longer or 35 minutes longer, which notice 0 is not contained in this interval, which means that it's statistically significant, and we can use the confidence interval as a test to reject the null hypothesis. We would say that we have enough evidence to suggest that, based on our samples, that the generic brand actually outperform the name brand. We believe that on average they are outperforming as well, anywhere from 2 to 35 minutes longer, which is pretty impressive. So our conclusions: we had a p-value of 3%, so that was enough for us to be able to reject the null hypothesis in favor of our alternative, saying that there was a difference between the two. Even when it was two-sided, apparently. So maybe our original p-value, if it was one-sided, was actually 1.5%. It's probably what I'm thinking. Then our confidence interval would say, what was the difference? If there was a difference, well, we believe it's anywhere between 2 minute improvement to 35-minute improvement with 95% confidence, meaning 95% confidence intervals gathered with the same sample sizes and the same methods would successfully capture the true population proportion. Now, do we know if this one did? No. All right. Oh, yeah, I couldn't resist. Sorry. Yeah, it was Big D's first AA meeting. AA meeting. Get it? Yeah. Yep. I don't know what to say after that. All right. So two sample T intervals for the difference in means. It's based on Pythagorean theorem of statistics. We've got our confidence interval here. We take the difference between the two. Usually we put the bigger one first, or one we expect to be bigger first. That way we have a positive value, plus or minus our margin of error. This comes from our critical value multiplied by standard deviation, or the standard error of the difference between the two samples, which is given by the Pythagorean theorem of statistics. Also keep in mind, even though we're subtracting the difference between the two, it's still adding variation when we subtract, not subtracting variation. We wish it subtract variation, but it doesn't work that way. You're just adding more variation by adding another random event or another step in the process. All right, all that good stuff. You're good to go. Conditions for two sample T interval. This is pretty important. So randomization condition. So our experiments must have randomly assigned treatment groups. Observational studies and surveys must randomly select the participants. Otherwise, we don't expect to be representative. And in experiments, if it's not randomized, we could have lurking variables and confounding that's going on. So we can't allow people to choose the treatment groups. Otherwise, I would choose the no exercise and dessert group every time. In fact, I just ate cheesecake and I don't even feel guilty. All right, 10% condition. I gotta, while this metabolism thing is still going for me, I gotta make sure that, I take full advantage of that. 10% condition. Usually don't check this unless the population is very small or the sample is very large, because most of the time when we're sampling and we're taking averages, we're like, even with CEO data, it's really hard to get a sample of larger than 200. And so most of the time we're sampling less than 10%, so we don't really have to worry about it. But if our population is really small or the sample size is very large, then we might have to worry about that. So remember, 10% condition is overriding the independence assumption, because we're not actually independent when we're sampling without replacement. We've talked about that a million times. Nearly normal. We're talking about the population here. We want to check the histograms of the samples to make sure we believe that the populations were nearly normal. But even if the samples were skewed or bimodal or something like that, or we think the population's skewed or bimodal or unimodal, it's still okay as long as we're sampling large enough. Like a sample size of 6 could do the central limit theorem's kicking in even with a small sample of 6, and it's going to straighten out skewed data. As long as it's only mildly skewed, it should be totally fine. But if we have really skewed data like CEO data, then we need at least a sample size of like 100 or 200 in order for the central limit theorem to kick in and to be able to straighten out those sampling distribution models so that it's still able to use a bell curve. Otherwise, you're going to have residuals of the population shape still affecting the sampling distribution models. Independent groups. So now we have 2 groups going on here. We cannot... this is because of the Pythagorean theorem of statistics. We cannot find add their variances together of the two different samples if the groups are not independent. So we have to believe that the 2 are independent of each other. So for instance, if we were talking about the average ages of when a husband and a wife get married. So when a couple gets married, right? What's the age of the husband and the age of the wife? Those 2 are not going to be independent of each other, right? Because older men are typically going to get married to older men, and younger men are typically younger women. I said that. Wow. Anyway, younger men are typically going to get married to younger women, right? So, so they're not going to be independent. Also, like possibly even taller people might be more likely to date taller people, and shorter people to date shorter people, and stuff like that. So those 2 groups would not be independent. So we'd have to be careful in that case. But with the batteries, we're totally fine because the performance of one group does not affect the other one. But just don't forget that important condition. And we will learn later, I believe next unit, how to compare means when we have paired samples or blocked or paired samples. So like before and after of the same individual or 2 people that are related to each other or something like that. We'll learn how to do it, and it's actually pretty powerful. So that'll be one of the last things we do. So 2 sample t-tests. So with the t-test, our hypothesized difference called the delta knot. Delta is just a capital Greek letter D, basically delta. It looks like a triangle, but it just means the difference. So the hypothesized difference is delta naught. Okay. Usually our delta naught is 0. So we use the statistic where we're taking our sample difference, the difference in our samples, minus what we thought they would be, which is the delta naught, the hypothesized value. We assumed they were the same or something. It's almost always 0. And we divide it by the standard deviation or the standard error for the sampling distribution models between the difference between those 2, which again is found by the Pythagorean theorem of statistics. All right, so that's that. I think we're done. So 34 minutes. If you notice, the first lecture of any new chapter is always the longest one because I got a lot of new stuff to show you. Then after that, we kind of go through things a little bit quicker. So bear with me. Thank you for making it all the way through the video. Whoever's watching, I appreciate it. And I'll talk to you guys tomorrow.